Hi, I'm Jocelyn Chen from the University of Texas, Austin. Today, we're going to talk about the multimodal regular expression synthesis technique. This is joint work with Xunyu Wang, Shi Ye, Gure Duret, and Ishil Dilik. As a convenient mechanism for matching patterns in text, regular expressions have been widely used in numerous applications such as text searching, stream processing, input validation, and file searching. However, despite regex being super powerful, regular expressions have a reputation for being quite difficult to master. This work is about automatically generating regexes so that people don't have to do this manually. Since writing reg is such a tedious work, we're not the first one to do this. Let me give you a bit of context by talking about prior works. Prior research has proposed methods to generate regular expression from high-level user guidance automatically. The main technique I would like to highlight here are enumerative search using positive and negative examples, and machine translation models such as seek-to-seek that translate natural language specification to regex directly. However, the first one suffered from restrictions on syntax, for instance, restricting the use of clean star on considering only binary alphabet. The seek-to-seek model can only achieve with relatively low accuracy because natural language is by nature ambiguous. While all these models only uses one type of specifications, in reality, we observe that people often use both the natural language description and positive and negative examples to specify their desired regex. Let's look at Stat Overflow example, where the user is asking about how to write the regex. As you can see from the post, the user first gives a brief natural language description to describe the overall structure she wants. Then she provides some positive and negative examples to further specify the behavior of the regex, just in case the natural language description has some ambiguity. Since providing the natural language description and examples is a natural way to specify the regex, it is apparent that we can do the same thing to synthesize regex too. In this work, we present a regex synthesis tool, Rego, that takes two modalities of specifications: natural language to capture high-level intention, and positive and negative example to eliminate spurious programs. Here's Rego overall workflow. First, we take the natural language description provided by the user to a sketch generator. They output a set of candidate sketches. Then, we input the sketches and the example to the synthesizer. Instead of returning a first finished result, the synthesizer will return the first K result finished and ask the user to inspect the outputs. If the user finds that they want, that's great. However, if they decide none of the result is the one they want, they can always invoke the synthesizer interactively by providing more examples until they find a satisfying answer. In the following talk, we're going to discuss each step in more detail. To give a bit of context, we first describe the domain-specific language we use in Rego. In order to have a more readable language compared to the standard regex syntax, we use a DSL that's similar to prior work, while making sure that this language is as expressive as a regular language. If we're taking the ground truth answer in the previous Stat Overflow post and we write it in our DSL, this is what it looks like. The first part of this regex is repeat range constructs, which means repeating a number from 1 to 15 times. And it is concatenates with another regex, which is an optional dot followed by a number matched 1 to 3 times. The first step in Rego workflow is sketch generation. Here, we're parsing natural language descriptions into sketches. The sketches used here are similar to typical sketches, which are partial programs with holes to represent the unknowns. However, unlike typical sketches, here for each hole, we allow it to have some components that represent possible subprogram that could instantiate this hole. In terms of the syntax, we use a square to represent the hole, and the subprogram inside the curly bracket are the components. Let's see an example of the sketch. This is a simplified natural language description from the running example. It can be parsed into a sketch where the root node is a concatenate operator, and each of its arguments is a hole with 2 components. The way we're going to generate these sketches is through semantic parsing. For those of you who are not familiar with this term, semantic parsing is a technique from the NLP community that allows you to translate the natural language description into a so-called logical form. A logical form is an unambiguous language that is specified using context-free grammar. In our case, we represent logical form as sketches. More specifically, our semantic parser defines a set of reduction rules that describe how you derive non-terminals in the context-free grammar from token sequence in the English description. In a general case, we all know that natural language is highly ambiguous, so there may be many sketches associated with a given natural language description. So the key idea here is to use machine learning to predict the most likely logical form from the given description. As we mentioned in the overall workflow, in our setting, we output not only a single sketch, but also produce a ranked list of sketches. The reason that we choose semantic parsing instead of a deep learning technique is that semantic parsing is less data hungry, so we don't have to find much training data to generate sketches. So once we generated all these sketches using semantic parsing, the next step is to generate all sketch instantiation that matched all the positive examples and reject all the negative examples. At a high level, we use a sketch-guided enumerative search algorithm. Although the sketch derived from a natural language is very helpful, it is still challenging to find a satisfying instantiation because the Regex search space is still quite large. To further speed up the synthesis, we developed two techniques. First, a technique that decides whether a partial Regex program is feasible, and second, use an intermediate representation to reduce the search space further. First, we describe the technique we use to decide whether a partial Regex is feasible or not. So given partial Regex P, we generate two concrete regexes, R plus and R minus, such that R plus can match those strings that can be matched by any regex in the space of regex defined by P. And R minus can match those strings that can be matched by all the regex can be instantiated from P. Therefore, the idea here is that if there's any positive example cannot match by R plus, it is safe to reject it. And if there is any negative example matched by R minus, we can also prune this partial program. Thanks to the natural language description, we can generate precise R plus and R minus using components that have a lot of pruning power. Now let's see some simple example of how we construct R plus or R minus applying the infeasibility check technique in the running example. Given the sketch generated from the natural language, in the first example, we instantiate the first hole to be one of its components, number, and obtain a new partial program. Suppose the hole can only be further expanded once. Since we know that either of this component can only replace this hole, we create an R plus by replacing the hole with the OR construct with the components as its argument. Note that this regex cannot match any positive example, so it's safe to prune it. We'll use a similar strategy to create R minus for the second example, where we instantiate the first hole to be the number and the second hole to be the construct not, and leave this argument with the hole with components. Using the semantic of the not operator, we know that any program that can be instantiated from this partial program will not be able to match repeat range number 1 to 3 times or comma. Note that R minus here accepts the first negative example, and therefore we can prune this partial program. In these two cases, we're able to prune partial program without further expanding the holes. The second idea underlying our synthesis algorithm is to introduce symbolic regex to prune large parts of the search space. Recall that our DSL has several constructs that involve taking integer constants as arguments. Explicitly enumerating all the possible values during synthesis will be really inefficient. For instance, a sketch with 3 repeat range construct where the largest integer argument allows 15 has 10 to the power of 6 possible programs just from this single construct. To deal with this challenge, we introduce the concept of symbolic regex, where everything in the program is concrete except the integer constant argument and repeat family construct are symbolic. Here's an example of the symbolic regex. Notice that we use the symbol kappa as an integer argument in the repeat construct to indicate this is a symbolic constant. In this case, we're able to avoid explicitly enumerating all the integer constants. Now we have the symbolic regex, we still need to obtain all the possible instantiation of the symbolic constants in order to synthesize a concrete program. We first generate an SMT formula that encodes the constraint in terms of the length of the string it could match. Note that this constraint is over-approximated in the sense that it should satisfy the length of the positive examples provided, but there's no requirement on the negative examples. Let's look at two simple examples to show how we do the encoding. Here, let x be the length of the string matched by the regex. Our first example is a start with program where its argument r can be matched by a string with length x1. Since we know that the start with construct needs to at least match what is matched by this argument, the length of the string that this regex could match should be at least x1. Our second example is a symbolic regex with repeat at least, where its argument r can match string with length x1. Since repeat at least concatenate at least kappa copies of R, the length of the string can be matched by this regex is at least kappa times x1. Once we get the constraint, we pass it to the SMT solver to get the possible value of the symbolic constants. We'll not go over in detail how the symbolic regex work, so let's just go over a running example of how we use symbolic regex to prune the search space. Take a symbolic regex and set up positive and negative examples. We first encode the symbolic regex to obtain the constraint phi. Recall that x represents the length of the string can be matched by the regex, and we'll give an upper or lower bound for x in this formula. Since the longest example provided has length 18 and the shortest has length 7, we use these to instantiate phi and a simplified formula psi. We then pass this formula to an SMT solver and returns the model, which here is that kappa 1 equals to 1, kappa 2 equals to 12, and kappa 3 equals to 2. Note that we have already avoided enumerating infeasible values such as all kappa equals to 1, since otherwise you'll never be able to match the longest positive examples. Recall that the general formula over-approximates this regex semantics, so we still need to check if a solution satisfies the given examples. To further improve pruning power, we obtain a new partial program by partially instantiating the symbolic constant with the value returned by the solver. We check for the infeasibility of this partial program, and it turns out that this program cannot match the shortest positive example. We therefore, instead of pruning one single program with all the value instantiated, prune all the partial program where kappa 3 is 2. To summarize, here's the overall workflow of completing a sketch. Once we obtain a partial program through enumerative search, we check if this partial program is feasible or not. And once we obtain a symbolic regex, we solve for the symbolic constant in the regex and output the concrete regex when we find an instantiation that accepts all positive examples and rejects all negative examples. So that's all the technical details I have, and now I'm going to switch gear and tell a little bit about evaluation results. First, we evaluate the benefit of multimodal synthesis. Specifically, what is the benefit of having natural language descriptions and example as specifications simultaneously? To evaluate this, we use two datasets. First, a subset of the existing deep regex dataset that consists of natural language and regex pairs. In order to evaluate our technique on this dataset, we need positive and negative examples in addition to the English description. Thus, we take 200 benchmarks from this dataset and ask users to provide positive and negative examples. Second, we collect 122 benchmarks from Stack Overflow that contains both the natural language description and positive and negative examples. We compare Rego with two baselines. Rego PBE, which is a variant of Rego that only uses positive and negative example, and Deep Regex, which is a seek-to-seek model that translates natural language to a regex. Since the PBE tools are designed to run interactively, we start invoking a synthesizer with an initial set of examples in the original dataset and providing two more distinguishing examples in the following iterations if they fail to produce the intended regex. In this experiment, we allow up to 5 iterations. The graph on the left shows the number of benchmarks solved in each dataset across 3 tools. Here I define a benchmark to be solved if it gets the user intended regex. As you can see, among the 322 regex tasks, Rego solves 80% of the benchmark, but Deep Regex solves only 43%, and the PBE only baseline solves only 26%. To evaluate the effectiveness of PBE engine, we do an evaluation study that allows us to quantify the impact of the pruning technique described in the technical part of the talk. We consider 2 baselines here. Alpha Regex is a state-of-the-art example-based regex synthesis algorithm that uses breadth-first search and pruning. To apply the algorithm in our context, we implement a sketch-guided enumerated search synthesizer with pruning technique proposed in the Alpha Regex algorithm. Rego with symbolic is a variant of Rego that does not leverage the symbolic regex idea to prune the search space. We run all 3 tools on all top 25 sketches generated for each Stack Overflow benchmarks and measure the cumulative running time with respect to the number of solved sketches. Here, we define sketch to be solved if the PBE engine can find an instantiation of the sketch that is consistent with the examples. It turns out that for the first 1,000 sketches that can be solved by all tools, Rego is around 10 times faster than Alpha Regex and 2.5 times faster than Rego without symbolic. Since Rego focuses on end user, it will be interesting to see whether Rego helps user complete regex-related tasks. To evaluate that, we conduct a small user study involving 20 participants, 5 of whom are professional software engineers and 15 of whom are CS students. Each participant was provided with 6 Regex tasks, random sample from the Stack Overflow benchmarks. Then, we provided each participant the original Stack Overflow post, which contains both the natural language and the example, and asked them to solve half of them using Rego and half of them without. One thing to be noted here is that we do not specify any specific way that participants should use Rego, but just provide the tool and educate them how to use it. The participants have 15 minutes to finish each setting, and we evaluate the effectiveness of Rego in terms of the percentage of benchmarks solving each setting under a time limit. It turns out that Rego users are 2 times more likely to construct the correct regex using Rego compared to those without access to Rego. To conclude, today I describe a multi-modal regex synthesis technique using both example and natural language description as specifications. The key idea underlying our approach is to parse the natural language into a sketch with components to capture the intention and to guide the search, while using example to handle ambiguity of sketches. We're able to synthesize 80% of the user intended regex across 2 datasets. Rego is publicly available under this link, and I'm happy to take any questions. Thank you for listening to the talk.